University next. We are hesitant to have a.
We can start our session. We have our translators online.
Published in BBC with 20 samples. Yes, they did. So that, yeah. But then they were in trouble with the government. So now the government.
I hear. Can you mute Anna? I think it's coming from Irina Dobrenka. Is it possible for you to? Because we heard this sound. I think now it's gone. Okay. All right. So good morning, everyone. We will start the first session today. This will be given by joint speakers, being Ilse van Keer, Jan Bronders, and Wart Swinnen, all from Vito. It will be a long morning course, but we will take several breaks in the meantime. So I think if I'm right, I don't know who the first speaker was, but I invite you to, it's you, Jan. Okay, so I invite you to share your screen, and then good luck. And please, in the meantime, don't hesitate if you have questions to put it in the chat, or also during the Q&A sessions and the breaks to ask your questions to the presenters. Thank you and good luck.
Hey, trying to share my screen. Okay, I think the screen is visible for everybody.
Yes, it is, Jan, but not in presentation mode.
Ah, okay. How do I do that?
I think you have this icon.
No, I pressed that.
Yeah, but then maybe it's another screen of yours that you can have to share. I don't know how many screens you have.
I get some help here.
Ja.
Okay.
Niet als je met twee schermen zit. Kun jij anders je PC één scherm maken?
Ah ja, oké. Moment, hè.
En pak dan eens, of duplicate, druk misschien op.
Ah ja, nu staat hem op extend. Oké.
Ah, maar je hebt uw dingen.
Yeah, it's fine, Jan. Now we have it in presentation mode. It's good.
Okay. So, good morning, everybody. I'm Jan Bronders from Vito. And the first session will, the subject of my first session will be Introduction to Soil and Groundwater Characteristics. It's going to be a rather theoretical session, but all the things I'm going to tell you are necessary that you understand them to be able to follow the rest of the sessions, because all the terms and the parameters which I will identify here in my presentation, you will need if you go on the field, if you do analytical measurements, if you do field research, or if you do interpretations. My session contains of 4 chapters. So I divided my slides in 4 pieces. And the first one is about general characteristics on soil. And we will take most of the time on this chapter because that's the most important one, which we will have to look at the next days in the sessions. But I also give you some background information on groundwater systems, on the principle of source path receptor, meaning that the pollution is reaching some place where it's going to be damaged, where there's going to be some damage. And then I will quickly give you an introduction about characterization on soil and groundwater pollution, meaning the parameters and the things you have to look at when you are taking a sample or when you have to make a plan of sampling. So all these 4 chapters I will present one by one, and I will have a little break after the first one, which will take us about half an hour. So the first thing is that everybody knows the meaning of soil. It's the interface between the atmosphere and the lithosphere. It's the part which we are working on, which we are living on, which we are producing our food, which animals are living. And of course, in the sea, there is no soil. You only have soil on the continent. And the soil is a very important part of the biosphere. So all elements of living are using soil. That's why soil is extremely important, although in many countries it's not really taken as an issue where you have to look at. So it's becoming more and more an issue. Also with carbon problems and CO2, we are more and more looking to soil to see if solutions of that type of problem can also be found in soil. So what is soil? The first thing is we are trying to find and give you a definition. From a geologist perspective, I'm a geologist, it's only the upper part of the soil. So it's the piece where you find living creatures, which is on the top and which is not the original material. You will see further on, we will talk about the geological subsurface, and there we are talking about the original mother material which was creating the soils. Most of the time we are looking at the top. Of course, we will have to look deeper. You will see that later on. But the topsoil is only a few meters. And that's what we are mainly looking in. If we are looking at pollution of the topsoil, we are talking about 50 centimeters to a few meters. It's depending on the location where you are looking at. And you always have to remember that the soil is created, is a product of the weathering of the underlying rock. So the parent material in the area where you are looking at is the original source of soil. A little bit further up, soils are, of course, a result of weathering. And we have the pedology, which is studying. So you have geology, which is studying the deeper soil. And you have pedology, which is studying the topsoil. So if you are looking for an expert in soil science, you have to look for a pedologist. Important factors of the forming of soils, like I mentioned, is the parent material. If you're living on a volcanic island, then the soil you will find on the volcanic island will result from the erosion of the volcanic material. If you live in the Alps, the soil you're looking at will be a result of the erosion of the hard rock which you find in the Alps. Of course, there is also time, climate, and flora and fauna which also involve in creating and changing soils. Soils are continuously changing. Then I come to my first definition, which I found in the literature. And the first one is a bit very theoretical. So you can read it. I'm not going to read that. You can read it yourself. But I made my own definition, which you find in the lower part, which I found a bit by looking in the internet and changing some words to make it a bit easier and understandable. And for me, the soil definition is soil is the upper layer of the earth in which plants grow. They are colored, black, brown, maybe yellow, and they are composed of a mixture of organic material, clay, and rock particles. Of course, you also have sand and loamy, but we will see how that definition will work out if you look more at the detailed composition of soils, which I show you in a few moments. So we have a definition now what soil is, roughly. There are different interpretations. If you ask a geologist, soil, he will say, well, it's nothing special. You take it off and I see the real geology. If you see a pedologist, he will go exciting because he wants to study all what's happening in the top part, where the most of the biology and most of our use of soils is happening. Then some extremely important definitions which you have to take into account when looking at soils. In my figure here, I show a profile, so in depth, and you see on top the soil where the trees are standing in, and then you have a kind of zone which is called the Vedus zone. And this top part is partly the soil, but also partly original material. And you can find in this soil groundwater and air. and groundwater is filling up the pores. The pores are the little holes which you see if you take a sand. You see that the sand grains are not sticking together. They are loose, and the spaces in between the sand can be filled with groundwater or water or soil water. So that's why you see in my figure the Vedus zone is the zone where the particles and the pores are not completely saturated in water. If you go lower in my figure, you see a blue part. There you suddenly find a certain moment where there is a layer where everything is filled with water, and that's what we call the saturated zone. The saturated zone is the piece of the soil or the earth where you can find groundwater. And groundwater is in the pores. And between the Vadus zone, so the piece where there is no 100% water, and the saturated zone, you will find the capillary fringe, which means that some of the groundwater is sucked up in the top part, which is an important item for plant growth. Because the more and the thicker your capillary fringe is, the easier plants can put their roots in the soil and suck water from that part. So all these elements here are important that you understand them. The groundwater level can be very shallow. If you go to near a river, it might be 50 centimeters or half a meter under the surface. But if you go more uphill, it might be that the groundwater is 10 to 20 meters deep. And the groundwater is also fluctuating. So the level of this water table is moving up and down based on how many rainfall there is infiltrating and how many groundwater is flowing in from other areas. By other areas, I mean if you go to a mountainous area, you can have groundwater flow coming in underground into your groundwater system in your lower laying area. And if this flow is high, then your level of water will rise. And if it's dry season, then the water will lower. So that's an important factor which links us to the hydrological cycle. So soil classification is also made on the size of the particles. If you take a sand, you can feel with your fingers that the grains are you can feel the grains. If you take a clayey soil, then you can feel that it's very difficult to find the grains in a clay. So there is a kind of grain size fractions, which I show you on the left side of the slide. And to make this more visible, you can use this kind of texture triangle. And in the triangle, you see in the middle a little black dot, which is, for example, a sample which you took and you have made an experiment in which you can define the grain size, so you can identify in this graph for that location which type of balance between clay, silt, and sand there is. So it's typical to do that for any type of soils, and every soil is unique. It means that if I take a sample in Flanders or I take a sample in Ukraine, most of the time these things will, in this diagram, will appear somewhere, but they are different. So it's important that you also have a look at this type of classification, because it's defining how water is moving. It's also defining how much organic material can be found in some of the soils. And it's also defining how a pollutant will degrade or move into the topsoil. I go to another point, which is called porosity. I mentioned before, porosity is an important item because you want to know how much water there is available in your soil. Porosity is defining how much the capacity is of the water volume, how much water you can have in a certain soil. The equation here, you can find many equations, but this equation shows you that their porosity is the volume of pores, space, which are not saturated, it's air, and the space which is filled with water. If you are in the saturated zone, all pore spaces are filled in with water. It means you are lower than the groundwater level. If the number of the volume of your pores is not full, then you are in the unsaturated zone. Why is this important again? Because the water flow in the unsaturated zone is completely different than the flow in the saturated zone. These parameters you have to understand, because if you want to estimate or calculate or model how much water is going in and out your system in the unsaturated zone and in the saturated zone, you have to understand what porosity means. You will also see this factor again later in the presentations of my colleagues, because porosity is, for example, very important if you want to model the flow of water in your system. We have 2 sessions on modeling coming up. So this parameter, you really have to realize that it's important and that you have to take that into account. I've also made a little list there that, of course, if you have large pores, it's easy to drain. If you have small pores, then the water is less mobile. It's normal. The water is stuck between the small grains of the clay and they will not move. This is another type of presentation of how soil can be presented in a graph. You see on the x-axis that the diameter of the grains, it's in a log scale, but that's not really important. It's showing you that the 3 types of soil, which we roughly classify, is clay, loam, and sand. And you can see that they completely are different in grain size. It's a way of presentation. It's one of the choices you can make. You can use this one, or you can use the graph which I showed before. And quickly mention you will ask me, how can I determine all these soil particles? You see an exotic formula there. I'm not going into detail, but it's called the pipette method. And you see this person in the lab has some column experiments in which we have put some soil and they are mixed. And based on gravity, we will see how fast particles are sinking. And based on that, on the velocity of how fast they sink and this equation up there, we can define a kind of distribution if the sample you are taking is more sand, more loam, or pure clay. This is most of the time a time-consuming experiment, which is quite expensive, so we don't do it too much, but it's one of the methods you can use to identify what type of soil you have. Of course, an expert on the field can already define with his fingers and feel on the sand or on the clay type and have a rough estimation between clay, loam, and sand. I give you some parameters here of soil. And the funny thing here is that, roughly speaking, scientifically, it seems that they all have the same weight. It's about 1,000 kilograms per cubic meter. And they roughly have the same type of porosity. But that's confusing because not all the pores, if you see the 3rd column, you see the porosity. For example, sand is 0.35 to 0.6. And clay is 0.3 to 0.7. If you see this graph again, there is seems that there is not much difference, but in this case it is not taken into account that in clay there is a part of the pores which are not contributing to flow. It means the pores are completely isolated, so they are filled with water, but they are not joining the flow happening in clay. That's why we also make a differentiation between the total porosity, which means how many volume space is there in a certain soil, and which volume is taking the flow. Where is the flow happening? That's the effective porosity. So the effective porosity is defining how easy water is flowing through soil. You can find numbers. I took one table here, but there are many tables. You can see many tables in the literature. So if you have to go to a field and you know that there is some paper on that site or on this specific soil, it's best that you try to find those background informations and see what the type of porosity and effective porosity is for your case. There is a strong relationship between the soil and the hydrological cycle. Now we are coming to more water movement and what is happening with water falling on the soil and how it's moving into the system. And this very schematic overview here, I will identify some of the important things. Of course, if you don't have precipitation, there will be no water flow. So in the desert, there is nothing much to say about water flow because there is almost no water in the soil. So it's a completely different situation if you are in Europe, where we have normally rain very regularly. So this rain will fall on the soil, and the soil is the first part of the geological subsurface, which will feel the rain coming up on the surface, and then it will infiltrate. And the infiltration is one of the important things which will happen. If you have a sandy layer, infiltration will go easy. If you have a clayey layer, infiltration will go slowly. So if you have a clay layer, probably you will have a lot of overland flow, which means water is just flushing away straight to a lake, straight to the river, and only a part of it is going to the groundwater system. So it's important that you also realize that not all the water which is falling on your surface is going into the subsurface. It's only a part of it. If you want to model things or calculate, it is important that you understand how much water is going into your system, because this water will move possible pollution in your system, in your soil. So you have to make for every place a kind of hydrological balance. You don't have to do that for every small part, but in general, for your country and for the area where you are looking, you have to look how much rain is falling, what the climate is, how much water is evaporating, and all these elements you have to put together before you can understand how water flow is impacting the soil system. The relation to plants is also important, because plants are normally, in our conditions, we have plants on top of the surface, and they will also interact with the rain. They will also use water, and they will also buffer contamination. And they will absorb it, or they will help to decay it. So it's very important that you understand that if plants are present, they also play a role in this cycle of water movement through the soil, changing of the soil, and taking the different components, including pollution, in their system. The soil is also an interesting and an important biological habitat for gene pools. It means that nutrients and essential elements are stored and used and created and removed, and water is there, one of the important things. Everything is heterogeneous. You never have a soil which is exactly the same. And we always forget that in the soil there is also a lot of microorganisms living there. So a worm or a microbe or some other minor and small fauna and flora is also present in the soil. If you destroy that, then your soil will not be functioning as normal. So you also have to take that into account when looking at water and quality and pollution. Of course, there are other soil functions which are not maybe at this stage super important, but on a large scale, They are very important because soil is an interesting storage system for carbon. We have the CO2 problem, which is very popular today, and soils are one of the major soil CO2 capture systems which exist on Earth. They also a source of minerals. You can extract sand, you can extract minerals. So it's also something else which we use as a human, except next to our food production, we also use soil as landscape. We also enjoy a nice garden. So the soil functions are not only nature and agriculture, but as there is a large human interest in soil also. This is what I already mentioned. There's a combination of all the soil functions. For us, it's interesting to have soil which is of good quality because we want to produce food. There is environmental interaction, biological gene pool, the source of raw materials, and we need soil to put our buildings on. So if the soil is in a bad condition in any way, if it's geotechnical, physical, or chemical, that's something we should avoid or try to repair. Good. Something about soil quality, because that's what we all want to end up with. We want to have a good soil. So there are always chemical, physical, and ecological differences. And we have to look at it in the different uses we are going to do. As I mentioned, soils, if you forget about sand, loam, and clay, they're all composed of a set of components. And in the graph here, I showed you that about 45% of the soils are minerals. Okay, that's an average. That's an average, so it can change from place to place. Some places the organic material is 90%, but minerals, air, water, and organic material. So that's always an important factor. Why do I say that? Because organic matter is an important component to take into account if we are talking about pollution, because organic matter is a chemical agent which can do many things with pollution. And you will see that also in the modeling exercise, which we will show, or in the determination of the reference values for concentrations. You have to take into account if the organic matter is high or low. Some of the concentrations which are accepted or making the soil less riskful are depending on the organic matter. This is a list of components which you find normally in a natural soil. You see there is a list of typical elements. And of course, silicium and oxygen are the major ones because that's that quartz. Quartz is one of the minerals which is the source of our soil. So it's normal that oxygen and silicium are very much available. And the other list is also there. So you don't see any organic or components which are man-made. And that's where humans come in. We are using the soil for our food production or other things, and we add components which are not originally there. Oh, sorry. So organic matter is present in the soil, and you will ask me where it's coming from. Of course, it's coming from the millions of years that plants, animals are interfering with soil, and you have more organic matter in some places and less organic matter in other places. There are soils in the world where there is no organic matter in there because there is no life, or they don't have any interaction with anything with life. You also have microorganisms which are using the organic matter and changing it. So it's a very important activity that these microorganisms do exist in the soil. I mentioned that before. How does a soil look in the field? You see a kind of pit which was made And then the picture in the middle shows you how one of the soil profiles can look like. But this is not standard because, like I mentioned, soils are different all over the world. So it can be that you dig this type of pit in your garden is completely different. But you see different, what we call horizons in the profile. And what we do, there is a system in which we can classify and describe all these soils. Maybe you don't have to do that, but somebody else will do this or has already done. And it's important to see where these different types of layers are found. It learns you how much organic material there is. It learns you where the water table is. It learns you where the plants are moving. And it defines in which sections you have to take samples if you want to look what's going on in the soil. If you are only interested in biology, you take samples to see what the fauna and the flora is in there. If you are interested in a certain pollution or a certain component, you can see in which depths you have to take a sample. I have some other slides showing similar things, but the idea is that you understand that there is a kind of classification with numbers, with letters, and they all have a meaning. So in that way, you need an expert in soil expertise. But it's important that you also know that if you do this on the field, when you take samples, that somebody can help you or look at this in a more scientific way and help you explain how these soils were built up and where the important layers are found. Now, how do you do that? If you really want to do a soil description, then of course you should learn what the codes are, right? A, B, C, that's in function of the depth. C is the parent material. And interesting is that parent material, as I mentioned before, that is the soil type of the composition of the earth, which is lower than your soil profile. And this was the original soil type on which your new soil, the top one, the dark pieces, are formed. So in this case, I guess it looks like a sandy layer. It means that the top part is also sand, but it's mixed with organic material and all types of mineralization, which is infiltrating from the top into that part. When you do a description, it's important that you look at the elements which I list up there. It's the thickness, the color, the roots, whatever you can see in there, you give that in the vertical profile so that anybody who has to go back to that site has a good description of the soil. Of course, there is a large variability in vertical and horizontal and the place where you are going to be. So you have to check every time if you go to a new area, make a borehole and see how much things are changing. And things will also change in time. Example is if you have agriculture, it might be that the first year there is maize, the next year there is grain, the next year is potatoes. And with climate change, you can have maybe more rainfall in the winter and a dry summer. That's all impacting things of your soil. Example here is, you see on the right side, it's a dry soil, and on the left side, it's a wet soil profile. And you see that they are completely different. And they can be in the same location. If you go a few hundred meters to the river, it can be a wet profile. And on the top, it can be a dry profile. So don't underestimate the effect of topography and hydrology if you look on the field, and that it can change in the same area, in the same soil. Another example is what I mentioned before. The left one is a mineral soil. It's nothing, there is not much of a organic material. And on the right side, it's like a peat layer, and it can be meters because you see the shovel on the lower right. So it can be organic material, a purely organic material. So soils are changing place to place. You have to check all this. A short word about the way chemical changes are taking place. I'm not going into detail, but there are theories and chemical explanations of how soils are changing as a function of time. So if you want to go in real detail and want to know how soil is changing, then you have to look at all these chemicals, look them up in your analytical exercise, and then try to figure out which changes are caused by metal or other activities in the soil. Well, I end my part on soil that soil classification exists, so you don't have to invent that. There is also an FAO standard. There is also, in different countries, there are different standards, so you can have a look through Google or internet. And on the left side, I put a nice picture on a composition of different soils. And you see that indeed they all differ. They have a different color. They look different in size. If you feel them, you can describe them already. So if you go on the field and you collect the soils and you put them in boxes like this or in little bags, you can take them to the lab and you can easily describe them and figure out and make a nice description that you know later on which type of soils you have been looking at. This is a similar reference, and then there is also a world map on soils. Maybe that scale is not really detailed enough, but I'm sure on every European country you can find this type of maps available on internet. And if not, then you can define this yourself by doing some field work. Okay, so I would like to end my first part here. I propose we have a 5-minute break. So if there are any questions, you can ask them. I also put my email address at the end of the presentation. So if there are specific questions, you can always mail them to me, or we can see how we can organize this in a more general way and see how we can collect all the questions. So I see you guys back in 5 minutes, and then we'll start the next sessions.
All right, thank you very much, Jan, for this really nice presentation. So if there are any questions, as Jan said, you can or email them afterwards or put them now in the chat or just ask and then see how we can answer. I think everything was very clear, Jan.
Okay, thank you. I'll just wait 1 more minute and then we go back to our...
Okay, I got the question, Jan. What is the difference between terms regolith and soil?
Well, regolith is the geological term for the original rock. Everything what's under your feet is regolith, and the soil is only the top part in which we work and live on. Regolith is in fact a more scientific term to make it more difficult. Is that okay?
I think so. Okay, let's wait if there are more questions pumping up. Yeah, it was clear. Okay, Jan, I think there are no more questions. So if you are free to go, you can continue with the next
part. The next part is more focusing on groundwater. You understand that we were looking at the soil part, which is mainly what I call the unsaturated zone or the Vedus zone. Now we are going to look at groundwater. I come back with a figure where you find a similar profile as I showed before, but now I'm focusing more on what is in the blue area. You remember my first figure, which was divided in an orange piece, which was the Vadus zone, unsaturated, and the blue part. In this picture here, you see a similar situation in which the blue is showing what we call an aquifer. The term aquifer is very important that you understand that, because it's a scientific name for a geological water layer where water is moving. Moving, it means flowing, and also in this case you see a pump or a filter. It's a pipe which is installed in the subsurface in which you can take out water from that aquifer. You see also on the same picture a term aquitard. Aquitard is more like an impervious layer, a clay layer. And in my profile here, I have a clay layer on top and below the aquifer. That means this aquifer is confined. It's blocked between two pieces which are impervious. In any other system, you can have no aquitard on top, and you can have no aquitard down there, and you have a huge aquifer where you can have lots of mass of water moving downstream. The connection to the soil is given in my little picture here. On top, we have the soil. It's called the soil zone in this case. And water is infiltrating towards the water table, which is lower in the soil profile. So the infiltration will take time. So it will flow downward. And depending on, first of all, the type of soil, sand, clay, or loam, and the thickness of this zone of aeration, which is another name for the unsaturated zone or the vadus zone. So we can all start to become confusing about all the terms these scientific people are defining. But finally, this water will end up in the water table. So why is this important? Because the water which is infiltrating will take your pollution, if there is any pollution, toward the water table. And in the water table, the water will move, it will flow. You also see a bit...
Ja, maar niet om dan 10 uur te beginnen spreken.
Ilse. There is some noise here. You see also a strange piece in the figure, which is the perched water table. You see on the right side, there is a little blue part, which is hanging in the unsaturated zone. It is possible that your unsaturated zone also has a different composition, and that you find little clay layers hanging or sitting in this unsaturated zone. And then on top of this clay, it is possible that water is stored. And you see then this perched water table. This type of system can also be very important in agriculture, because it's a change of water balance in the zone of aeration or in the unsaturated zone. This about the situations which you have in the soil. Now some explanation about movement of groundwater. I already introduced you that precipitation will fall on the surface, will infiltrate. It will take time before this infiltrating water will end up at the water table, and then it will start flowing. There is one big definition of groundwater flow, which is extremely important. Water will flow, as you know, everybody knows it, from the higher potential to the lower potential. It means it will flow from the highest water pressure to the lowest pressure. Why do I say it like that? Because there also exist places where the groundwater flow is in the other direction and topography, because there is a change in pressure. But that's special cases. You see in this figure with the arrows that my groundwater flow in this picture is flowing towards a river. The speed of the flow and the way and where the water is going to is depending on the soil type, on topography, on the draining capacity of the river, and all these combinations will make that a flow is fast or slow. The river, in most of the cases, in our areas in Europe, is what we call a receptor. The groundwater will end up in a river, and when this groundwater is affected by a pollution, the pollution will end up in the river. And that's a situation which we don't want, because if it ends up in the river, it will go in our complete ecosystem. And we have to take care of that. A river can also be a small ditch. So if you have a parcel of agricultural area, it might also be that the ditch next to your parcel is affected by polluted groundwater. And then you bring your pollution back into your system, because most of the time we are using this same water for irrigation and we bring it back on the land, and then it's a kind of circle and you always move around and you make it spreading and higher concentration. So these are things which are depending on the understanding of groundwater flow. So there is one parameter which I didn't mention, and that's a kind of parameter which was determined by this guy on top. I don't know if the picture is really the man, but he did an experiment with a column, and then he found out that there was a relation between the type of soil and the volume which came out if you install a certain level difference in water. That's why he used a water column, because he wanted to show that water is flowing from the highest level, highest potential, to the lower. You see the column, and you see a little box on the left, and on the downward piece of his column, there is a little tap, and when he opens the tap, the water is flowing out. And he found out that this water is flowing faster if he used sand than if he used clay. Well, you will say that's normal because clay is less permeable. That's correct, but he wanted to find a number, a parameter, which is defining how easy water can flow through your system. This is a basic law, it's Darcy's law, and it's the basic law for saturated flow. Saturated flow of water in a geologic system, including soils. You see this famous equation there. It is a simple one, because next I will show you extremely difficult equations, because we are going to look at pollution too. What do you have to understand from this is that there are a few numbers here, and symbols, like the Q is the flux. Flux means how much water is flowing through a certain area. And this flux, more water is flowing if these two numbers are high, K, and this gradient, the delta H, is the difference in groundwater level. For example, if you are standing on a hill, the water level which you measure under your feet is higher than the level of the water which is in the river, which is 200 meters further. So delta H is the difference between the water level on the hill at the river over L, which is the distance. And then you have this parameter K, which is called the hydraulic conductivity. And as I mentioned before, it's the measure of soil's ability to transmit water. That is something, if you want to do a risk evaluation on your field or on a certain area, you have to know this value for all the layers you are considering. You can measure them, but normally there are general indications of how much this number will be. So try to remember this law, Darcy's law, and more specific, the term hydraulic conductivity. There are tables, and this table is maybe not the best educational one, but you can find in the literature different lists of hydraulic conductivity values. In this case, the hydraulic conductivity value is given in meters per second, centimeters per second. I prefer meters per day because that's something you can more realize. And depending on how big this number is, you can define here permeability. In this range, it's pervious. In this range, it's semi-pervious. And in this range, it is impervious. It doesn't matter if you are using centimeter per second or if you are using meter per day. It's a definition which you can always use. If we go to the terms which I used in my previous one, aquifer means it's a very good water-bearing layer, and you compare that to the different terms, permeability, then you find a kind of definition. These are good aquifers. It means there's good flow. You can even put a well in there. You can pump water, and the water will easily flow to a river. If you go to this piece here, it's a bit less. It's not so interesting. And if you are going here, then you don't have an aquifer anymore. You almost have an aquitard, which is going to be a layer which is almost impervious. Then you can do the same for soils. As I mentioned, sandy soils and gravel are extremely interesting for aquifers. And the more you go to the right, the more clayey or less permeable. There are some other types of aquifers like clayey layers, but also chalk layers can also be very impervious. Look this up if you need it. There are many other tables, maybe better than this one, but the K value is an extremely important parameter to define if your soil or your aquifer is useful and interesting for water flow. I make a quick shift to the groundwater and the pollution problem, because what we are trying to do is finding all the elements which we need to interpret how a contamination is moving in the topsoil, but also in the subsurface. My schematical sketch here shows some possible sources on top, like a landfill, or fertilizers and pesticides, or a septic tank, or an industry is not mentioned here, but they all have possible sources of pollution which move through the subsurface and end up in your groundwater system. And if you, for example, have a well where you pump for drinking water or you pump for irrigation, that well will be damaged. That's one of the receptors. I'll come back to the principle of the receptor later on, but I already told you that a river is a receptor, but a groundwater well is also a receptor. To define all this, we need a conceptual model, and the conceptual model, it's a sketch like this. You have to add all the parameters which you need, for example, how much water is coming in, what the K value is, what the soil is. So we are not looking only at this 1 meter top if we want to have a complete image of the problem of a certain pollution. Of course, we need to know what the sources are. In some cases, it's very obvious. In some cases, we don't know. We have to look at how it's spreading and what is actually available on the field where we are, and how the interactions are. That's a bit similar as I already explained. Now, what are different possible sources of contamination? This is a sketch I also took from some internet site, and this gives you a very brief overview of what is possible as sources. If you don't know where to look for, you can start with this list and you will say, is my problem created by urban runoff? It means that water polluted from the streets, or some household activities which are by any means making some pollution. Agriculture is a big one which you have to look at. Sites where you have waste, abandoned wells, that's also a problem, because at some places a well is abandoned and it is not protected anymore, so dirt will fall on, people will fill it up. Then you have some other elements on the right side which are in most places not important, like fracking. Fracking, I don't know where fracking is in there, but that's an underground geological method to remove oil from shales. Most of our countries in Europe don't have that. Underground storage tanks, that's important. Septic systems, and of course, chemicals which we use for everyday use, which we 50 years ago didn't realize that they were so important or so damaging. So we are facing these problems today, and we also have to look at this. It's important to look at this because finally you have to define which type of analytical activity. What do you have to analyze? That's important to know which parameters you are looking for. You should know what the source is of the contamination. Groundwater itself doesn't contain all these exotic parameters which humans already have introduced, but there is a list of parameters which you at least should look at if you have a groundwater. And this is the list of parameters which is normally standard analyzed to see if your water is which type. If you are sure that it's pristine water, which means natural, you can do an analytical exercise and see all these parameters. And there is a nice way of presenting that. It's again a kind of diagram. It's a bit similar as the one we have for the soil, but in this case, it will show you the different parameters on the triangle and the other figure. And you can identify with these little dots if you have a type of groundwater. You can put it on there. And so you can organize and classify types of groundwater. This is also important because the type of groundwater will also define a little bit of your chemistry and also the relation between a parameter, a pollutant which is coming in, and the chemical reactions which are present. And if this water is already in a certain condition that you don't have to do anything. Some natural groundwaters are polluted. Like we have Bangladesh, where they have heavy metals standard in the groundwater because the soil is containing so much heavy metal that the groundwater is polluted. So you also have to look at the natural condition of groundwater, and that's why you need all these parameters, at least in a few analytical exercises, to see if your groundwater base concentrations are available. So what is happening to solute transport? I took this slide from a colleague of mine because it's very difficult to explain a pollutant moving to the groundwater system. And what we do is we are looking at the train, and the train is the pollutant which is moving into the water, and the train is driving, and the solute is the passenger. So it means the pollutant can be a passenger. So they're all sitting in this train and they're moving along with the train. And the convection, that's a term which we use how water and pollutant are moving. Convection is the movement of the train. So the first thing, when the pollutant is in the groundwater, it will move by convection. It's by flow. If you have easy pollution, like some pollution which is nicely soluted, like a salt, you mainly have convection. It means I don't have to worry too much about other factors which are shown next. And I can say, this salt is moving as fast as the train, as the water is moving. But now, this pollutant is not doing what you want. It's moving in different directions. And in the train, the passengers, the solute, are moving. So the one which is in front will go to the toilet in the last wagon, and up, it's moving again. And that's what we call diffusion. Diffusion is a change of concentration, which is a chemical action where you have to take into account, especially with organic pollution. Pollution is very effective to diffusion. So you also have to look at diffusion. And then you have to, the dispersion, it's also a kind of movement. You have different trains running next to one another, and the one is a local train and the other one is a fast train. And it might be that one is faster than the other, and that's a dispersion. And then, of course, on the way, it might be that a certain pollutant is sticking to a soil particle. So it's like the train is stopping and some people get out and the train is moving. So there less pollution is moving. So all these elements you have to take into account. There are also people who die on the train. So it's a decay. So some pollution disappears. So I want to show with this slide and explain with this slide that pollution transport is completely different than pure water transport. Our easy law of Darcy is not easy for solute transport. An important part of this, I will explain a little bit more in hydrodynamic dispersion, is a change of movement because of the grains. The water is moving through these grains, and you see on the left side different type of structures, and you see that the water is flowing around or straight, and depending on this type of flow, your pollutant will also move in different directions and move different left or right, and how fast it flows will depend on all these kind of elements. A quick overview in the surface, I mean in depth. Your vertical water flux in the left, in the blue, is changing, and you see the dark pieces are showing where the water is flowing fast, and the white ones are where there is no flow. And if you combine this kind of vertical view of a profile with a concentration, then you see again that the pollution is also moving in different ways, and you get kind of, well, a fragmentic movement and diffusion in the soil. And this is already complicated. It will become more complicated if I show you this equation, then you will say, Darcy law is very simple. This one you don't have to know, you don't have to understand this. You only have to know that if you go from classical flow of groundwater, which is easy, to a dispersion model, which means calculation of the way your pollution is moving, then you end up with this kind of equations, which is really a bit for more experienced mathematical people. Of course, people have done that for us. We can buy models, but you still have to feed and put data in there to allow the calculation to take place. A little bit about how are we measuring on the field. My colleague after me and the next days will also explain more. This is a bit of the link. How can we look into groundwater? And of course, everybody has seen a well, a concrete well or a tube which is standing in the field, and you can measure. On the right side, some person is measuring the level of the groundwater, and on the right side is measuring the level of the water, and on the left side you have an installation of a kind of sensor. You can measure things digitally, and most of these wells are composed of a filter and a screen, which you see on the right. This is a pumping well, which is also having a little shallow well to see the effects of groundwater abstractions in different layers. But this is the structure you will find on the field, which you have to install, which is called observation well or piezometer, which allows you to take samples, to describe the soil in deep, because the topsoil is only a few meters, but if you have to go deeper, you have to drill, and then you install this type of wells. You can also use this kind of monitoring devices, which we will show you when we do the field training. And then I still have a bit of, I'm seeing that I'm already at 1 hour, so I need another 10 minutes, Chris Groff. Is that okay? The idea of this slide here is the idea of the source path receptor. As I told you, the pollution is starting at a certain source, and it's moving to a groundwater, and it's then moving somewhere to a river or to a wetland. And that's what we call the receptor. If you look at an evaluation of pollution, you always have to look at where is the source, how is it moving, and where is it ending. And the ending is the receptor, and if the receptor is in danger, then you have to take action. The scale on which you have to look at is different. If you only want to look at the parcel scale, that's possible, but then the sketch which I show here will be much smaller, but it's always a conceptual model which you have to make for your application and take all these elements into account. There's another figure where you do the same, and in this case, you try to identify how much mass is flowing through the system. With all the equations I showed you, with all the ideas of saturated, unsaturated, the geological information, and the pollution which you measure, you can estimate how much mass, kilograms, is moving through a certain area and ending up in the river. It might be that this mass flux is so low that you don't have to take care. I mean, it's diluting and the pollutant is not really dangerous. Then it might be that you just measure and you observe if this is not getting worse. And if it's not, if it's getting worse, then you have to take action. So this is an exercise you will always have to do. And I combine this here. I will go through that. And my last part is a bit on the characterization on soil and groundwater pollution. And this a bit more into detail. As I showed you before, we have to see the pollution plume, and we have to look what kind of parameters we are looking at. And here is a little list in which, at least in Belgium, are a set of parameters you always have to look at. It's depending on the location and what problem you are looking for. You see a list there like the volatile organic components, PTEX and chlorinated hydrocarbons, oils, heavy metals, inorganic compounds, explosives, herbicides, and pesticides. Most of the time, it's a mixture of the whole lot. So you have to look at maybe a screening and see, I don't know too much. Maybe I have to look at only mineral oils and heavy metals. So it's really the history of your field and what is happening on the field and which type of activities were there or went wrong on that side that will define the analytical exercise. Some ideas about the properties. If you, for example, have an oil or a chlorinated component, these are elements which you have to take into account. It are the characteristics of the specific compound. Some compounds will not flow, some compounds will stick to the soil, some compounds will easily solute and will create large plumes. Some are biologically degradable. So these are things which you have to take into account. When you know which pollutant you have to take into account all these elements. Some other properties are given, like how much of the pollutant is sticking to the soil, how easily is it solved. These parameters you can find in the literature, but my colleagues who are going to present the modeling exercise on how to do a calculation of how the pollutant is moving will explain more about this and will also tell you when you need these parameters and how you will use that in the calculation. Similar here, how good is a retardation? How easy can the parameter be absorbed? Some of the sanitation or remedial actions, which you will also see soon in another lecture. It might be that your pollution is just sticking to the soil and it's not moving anymore. So that's items you have to understand. I will end my presentation by showing you two schemes of two types of pollutants, which are specific problems. And one is about mineral oils, And all the parameters I mentioned to you, like dispersion, dilution, the way the pollution is degraded or moving, is shown in this figure. You have a leaking tank here or an accident on top where oil is involved and oil is floating on top of the water. So it doesn't mean it is not dissolving, but it is floating on top of the groundwater system. So it forms like a pure product zone, which is very annoying, but because this pure product will continuously leach and you will have a continuous plume. So you have to understand the pollution which is present to know what you are looking for. So if you are looking at oils, you have to take this into consideration. If you're looking at a different type of product, which are the dense chlorinated components, they will sink. So they are not floating. So they will end up in your system in a totally different way. By these two pictures, I would like to end and tell you that if you're looking at pollution, you always have to realize that you have to know the system, make a conceptual model, look at the type of pollution, do proper analytical research, and then try to understand how the pollution is moving. Next to that, you always have to do a kind of risk analysis, and the source path receptor principle is one of the ways you can look at it. I'm not discussing about reference values or concentrations or risks. I think that will come in another session, but I think all the presentations I gave here will give you a set of information and ideas which you need, depending on which part you are involved, that you understand what is needed and already a little bit where and how you can do this exercise to combine all these data to do the total evaluation. So sorry for being 10 minutes over time, but I want to conclude here. You will find my mail address there on the last slide. So if you really have a question next days or something, you can mail me and I will answer you specifically on the elements which I have presented in my slides. That's it.
Okay, thank you very much, Jan. I will consider myself as a pollution next time I will take the train. Are there any questions now? Otherwise, I would definitely propose a 5 minutes break so that you can maybe have a coffee or use the restroom if needed. But first, if there are any questions, I think Jan is happy to answer them. I don't see anything in the chat yet, Jan.
Okay.
Is the next presenter, will this be Ilse or Wart?
I think so.
Yeah, okay.
Yeah.
So then at first I would say we have a 5 minute break for everyone. So you can, as I said, take a coffee, use the restroom. So at the 10:15, we will start the new session. Maybe in the meantime, Ilse, if you can check while doing the presentation, because I also saw, Jan, when you wanted to show something, the pointer, we didn't see your pointer. So maybe you can check, Ilse, with the no problem. It was okay, but maybe you can check in advance how to use if you want to point something in your presentation.
Yeah, I will try to share already.
Yeah, you can already share.
Wait.
Dear colleagues, we have a question about difference between terms of soil.
Can you see the pointer?
Yeah, we see the pointer, so that's working. Anna, you were saying that someone had a question for Jan?
Yes, in chat, read please the message about difference.
Because I don't see it. Maybe it's in the other chat, in the Ukrainian chat, because I can't see it.
Yeah,
Anna,
I also can't see it.
If you maybe can translate it.
what is the difference between terms regolith and soil?
Yeah, but that we answered in the previous, Anna. That was already answered. I thought it was a new question.
So let's be careful because
yeah, Ilse, we see your pointer, so that's working. I will make a comment for the other presenters as well. Yeah, okay. So we wait another 2 minutes and then we will start again.
Can you hear me well, Christophe?
Yeah, Ilse, yeah. The sound is okay. Yeah.
Okay.
And we see also your full screen, so you're in presentation mode as well. Maybe at the meantime, a question for you, Anna, as well. Is the translation working well? Is the speed of speaking and or are there any other recommendations or issues on the translation?
Mostly I was listening to English one, but Ukrainian as well. I was listening a little bit. It was working. Yes, they're changing.
Okay, that's good to know. Okay, so I see it's a 10:15. Ilse, if you're ready, so please, we go on with the next speaker, Ilse van Keer, who will tell you more about legal assessment frameworks related to soil and groundwater contamination. So please, Ilse, the floor is yours.
Thank you, Christophe. Good morning, everyone. First of all, I'd like to introduce myself. I'm Ilse van Keer. I've been working at FAO since 2000 in the field of soil and groundwater pollution. And I belong to the same team, research team as Jan do. Today, I will guide you through the legal assessment framework for soil and groundwater contamination. Tomorrow and on the 6th of November, I like to share my expertise with respect to soil and groundwater sampling. It's not moving my screen. It's stick. Now it's okay. Okay. So in the next hour, I'd like to tackle the legal assessment framework for soil and groundwater contamination in Flanders, including soil and groundwater quality standards. Also, what about EU soil legislation? The link between the EU soil monitoring law and the Water Framework Directive will be illustrated. And finally, an introduction of the basic principles of human risk evaluation will be given. But let's start with the legal framework assessment. So legislation is essential for addressing soil and groundwater contamination for several reasons, including the protection of public health, environmental preservation, legal accountability, and sustainable development. Without clear frameworks, it's become difficult to prevent, manage, or remediate contaminations, which can have long-term consequences for ecosystems, human health, and economic activities. So the legal framework tackling soil and groundwater pollution is a multi-layered approach that includes regulatory standards, liability principles, soil and groundwater investigations and risk assessment, and remediation strategies. So the legal assessment framework, however, is highly context-specific, reflecting local legislation, contaminant types, land use, and the characterization of contamination incidents, and vary from country to country and even from region to region. But overall, the existing legal assessment framework usually contain the following main components: legislation and regulatory standards, liability and responsibility, soil investigation and risk assessment, and remediation. Legislation comprises national and regional environmental laws to regulate contamination issues. Regulatory agencies or local environmental authorities oversee the compliance with these laws and standards and guidelines. Liability and responsibility encompasses the polluter pays principle and defines strict and joint liability. What does it mean, the polluter pays principle? The polluter pays principle means that parties responsible for the contamination are typically held liable for the cleanup. This includes the polluter itself, and in some cases, current landowners who may not have directly caused the contamination, but owned the contaminated property. Furthermore, legislation may impose strict liabilities on parties, meaning they can be held responsible for contamination, even if they didn't act negligently. In cases of multiple parties, joint liability may apply, where each party can be held responsible for the full cost of remediation. Legal frameworks regarding soil and groundwater contamination impose the execution of site investigations on a regulatory basis, depending on the activities taking place at the site or when land is being transferred. When the outcome of a site investigation defines the need for remediation, cleanup standards must be determined together with the selection of the most appropriate remediation technique. The latter can range from complete removal of contaminants to risk-based management, with monitoring measurements carried out on a regulatory basis. Part of the main components just be described will be discussed later on in this presentation, or will be the subject of one of the other e-learning modules. The Flemish legislation on soil and groundwater contamination is primarily governed by two pillars, namely the Flemish Soil Decree and its implementing regulation called VLAREBO, or in full words, the Flemish Regulation on Soil Remediation and Protection. Our legislation aims to prevent, manage, and remediate soil and groundwater contamination to protect public health and environment. Flemish legislation on soil and groundwater contamination sets out a clear framework for investigating, managing, and remediating contaminated sites. It ensures that polluters are held accountable and land transactions are regulated. So the Public Waste Agency, the Flemish Public Waste Agency, OVAM, or in short, the Flemish Agency, is responsible for waste management, soil remediation, and sustainable management of materials in the Flemish region of Belgium. OVAM plays a central role in monitoring and enforcing compliance with the soil regulations. The main objectives of the Flemish Soil Decree are to remediate historical soil contamination, which is defined as a contamination before the Flemish Soil Decree came into force, or to prevent and clean up new soil contamination. New soil contamination is defined as a contamination occurring after the Flemish Decree came into force. So different approaches are then proposed for these two types of pollution. Historical pollution must be remediated in case of risks. And hereby, the strategic objective is to remediate all historical contaminate in Flanders by 2036. With respect to new contamination, for all sites for which soil and or groundwater contamination data exceeds remediation values, then immediate action is required. And in summary, for the Flanders region, 29th of October 95 is the cutoff date for site investigations. So it's the date the Flemish decree came into force. And as already indicated, new contamination is subject to stricter regulations and liabilities, where historical contamination is handled with more leniency, though it may still require action depending on the outcome of the risk assessment. OVAM's mission is to strive for a sustainable waste and material management, a clean and healthy soil, and the aim for the transition to a circular economy. The key responsible in relation to contamination, the other parts I'm not going to talk about. We are not going to deal with waste and materials, but the key responsibility of the Flemish Public Waste Agency in relation to contamination are drafting and overseeing the enforcement of the Flemish Soil Decree, including the Soil Settlements Regulation. OVAM has to ensure that contaminated sites are investigated, are firstly identified, subsequently investigated, and, if necessary, cleaned up. OVAM also manages a soil inventory system, tracking contaminated or potentially contaminated sites in Flanders. And furthermore, OVAM coordinates soil remediation efforts, and they issue certificates once a site has been successfully remediated. So, current Flemish legislation and EU directives on soil and groundwater quality are mainly based on active sampling techniques for the purpose of concentration measurements to monitor the qualitative composition of soil and groundwater. Consequently, one of the common elements of European legislation includes the use of threshold values to assess the possible presence of soil contamination and the related risks. Overall, thresholds define the maximum permissible concentrations of specific contaminants or hazardous substances in soil, ensuring that the land remains safe for various uses such as agriculture, residential use, and recreation. So recently, the FAO organized a workshop, and in that workshop, it was indicated that several terminologies, like for instance, soil guideline values, trigger values, acceptable concentrations, and so on, are applied in soil research. So not only the terminology differs all over the world, but also the methodology to derive these values and the objectives related to the identified or the defined threshold values. So furthermore, the numerical values attributed to the different threshold values depends on national and regional legislation. To get an overview of the existing threshold values applied in different countries, the International Network on Soil Pollution, or INSOP, compiles a data bank with all available information about the different thresholds. In the next slide, I will focus on Flanders and I will give an overview on the soil pollution threshold values applied in Flanders. So the Flemish soil pollution threshold values are defined in relation to soil characteristics, and these are the pH, the organic matter content, and the clay fraction present in a soil. In Flanders, we differentiate between target values, guiding values, and soil remediation values, which roughly indicates the degree of contamination, going from a clean soil to a contaminated soil. So target values in many countries, and also in Flanders, they are also referred as background values, and they are given by the concentration of pollutants that can be measured in natural conditions. For natural occurring components, like heavy metals, the target values correspond to the observed concentration in topsoil under natural non-polluted conditions. For all man-made components or industrial components, this means that the target value should be 0. Unfortunately, this is not the case in our industrialized region, and therefore the target values of industrial components are set to the limit of quantification, or also called the LOQ, achievable with the imposed analytical techniques. Flemish soil remediation values indicate the level of soil contamination posing a significant risk of adverse effects to humans and environment. Soil remediation values are based on human and ecotox risk evaluation, considering concentrations of components, their behavior, and ecotoxicity of the pollutants. Another important parameter using to derive soil remediation values is the land use. In Flanders, we differentiate between nature, agriculture, residential, recreational, and industrial use, indicated by the Roman numbers A1 to 5. Also, the routes of exposure is very important, together with receptors, for instance, babies, children, adults, nature, and also the intensity or the time that there is contact between a receptor and a pollutant. The soil remediation standards are the assessment criterion for remediation needs in cases of new soil contamination. Important to mention that for the derivation of the Flemish soil remediation values, the protection of groundwater or other water bodies is not included in the methodology for the establishment of soil remediation standards. The determination of leaching risks and risk due to spreading is part of the risk assessment during a descriptive soil investigation and is addressed in the soil remediation project when setting risk-based remediation values. My colleagues Ingeborg Joris and Jeff Dams will explain everything on the spreading risk and leaching and spreading on contaminants in the session of tomorrow. So, a typical value also used in Flanders is the so-called guiding value. A guiding value is a value that is set between a target value and a soil remediation value, and it includes levels in the soil of pollutants in the soil, allowing the soil to be able to fulfill all its functions without any restrictions having to be imposed. Guiding values must be determinable with sufficient analytical precision. Guiding values for heavy metals are set at 60% of the type 2 soil remediation standard of a standard soil. A standard soil is given by 2% of clay content, a 10% of organic material, and a pH of 5. The way guiding values were derived for organic parameters is slightly more complicated. Basically, the guiding value is set at the sum of the target value with the soil remediation value of type 2 land use divided by 2. For some parameters, like for instance vinyl chloride, where the soil remediation value type corresponds to 5 times the LOQ, then the guiding value is set at 3 times the remediation value. At 3 times the LOQ. When the guiding value calculated according to these two basic principles exceeds 80% of type 2 soil remediation value, exceeds 80% of the remediation value type 2, then the guiding value is adjusted to 80% of the type 2 soil remediation value, for which the organic matter content is set at 1%. The guiding value will only be derived after the final decision on the target value and the soil remediation value. Also, for the groundwater, threshold values are defined, and they are still called also soil remediation values. And also here, a differentiation is made between target values, guiding values, and soil remediation values, indicating unpolluted groundwater to polluted groundwater. The principles regarding the groundwater target value are comparable to that of the soil, within respect that for natural occurring substances, the target value corresponds to observed groundwater concentrations of phreatic aquifers located in regions that are less as possible influenced by human activities. As already told you for the soil, for the soil values, for all man-made compositions, the groundwater concentration should be 0. Also here, this is not always the case, and therefore the LOQ is set as target value for the industrial components. The Flemish groundwater remediation differs a bit from the soil remediation values. The Flemish groundwater remediation standards have only a human toxicology rationale. They are independent of land use and have drinking water quality as criterion. The methodology behind the derivation of the guiding values is not known to me. And also not to my colleagues. So we assume that several years ago, this was a policy-based decision. So, and in the next slides, I'm not going in detail through it, but you find an overview of the Flemish soil pollution threshold values for a standard soil. So here you see the values for heavy metals, which a column indicating target value, guiding value, then the soil remediation values as a function of land use. The same here for groundwater, target value, guiding value, and one value independent of the land use. In Flanders, values have been derived for heavy metals, for monoaromatic hydrocarbons, for polyaromatic hydrocarbons, for chlorinated aliphatic hydrocarbons, for chlorophenols, cyanide, and also for a very few persistent pesticide for which use is now forbidden. And finally, here you have some values for MTBE, which is an additive of petrol and polychlorobiphenyl. When site-specific, so here's values are given for a standard soil. When site-specific values are given for the clay content, the organic matter content, and the pH, then the Flemish soil pollution threshold values have to be recalculated. Formulas are included in appendices of the Flemish implementation decree de Vlaardingen. If soil contamination contains parameters that for which no Flemish threshold values exist, then they need to be calculated by the consultant, or they can perform a literature study, and if possible, they can calculate using a model, for instance, in Flanders as risk is used, which is a state-of-the-art model for performing human toxicology risk assessment and for calculating soil remediation standards. So this was a whole bunch of how, according to the methodology of the target values of the remediation values. I'm not going in detail to these figures, but I tried to indicate which value is used. So here we see that for preliminary investigations of new pollution, then when soil remediation values are exceeded, a descriptive soil research investigation has to be carried out. When 80% of the soil remediation value when the concentration of pollutants exceed 80% of the soil remediation value, then a limited risk evaluation has to be carried out. If the comes out of this limited risk evaluation is positive, if there is no risk indicated, then no further actions have to be taken. If the limited risk evaluation indicates that there is a possible risk, then also descriptive soil research has to be carried out, even the soil remediation values are not exceeded yet. So in the same way, also the other tables are drafted, so you can have a look at it to see how the different values are used. The same for in the descriptive investigation. I'm come later to those two different researches, a bit different. There no 80% value of soil remediation value is used. There we are only working with target value and guiding value. When concentrations exceeds guiding values, there is no action required with respect to remediation, but the pollution contours have to be delineated, and also users' recommendation have to be written. When soil remediation values are exceeded, then of course remediation is needed. As said earlier, with respect to historical pollution, there we first have to evaluate the risk to carry out a thorough risk assessment, and only when the risk assessment is give possible risks, then remediation has to be performed. Okay, that was in short some elements of our Flemish soil decree. Recently, also the Ukrainian government approved a resolution for sand and soil monitoring. And this resolution is part of the state environmental monitoring system. And it states that all lands, regardless of ownership and source, are subjected to monitoring. And monitoring of land for soil contamination on agricultural soil includes, or agricultural land includes, agrochemical soil survey, control over changes in the qualitative conditions of soil, agrochemical land inventory, monitoring of soil pollution with pesticides, heavy metals, radionuclides, and so on. And this regulation of resolution gives also indicators and frequency for land and soil monitoring. So, but my question to you is, are there also procedures which accompany these guidelines on how to carry out and report these monitoring campaigns? Or is this work in process? Please, if you know more about it, put it in the chat. I will glad to be informed. The Ukrainian procedure for monitoring land and soil also contains standard values, and they differentiate between the total value and a mobile form. The total value indicates maximum permissible concentrations. the mobile or moving forms refers to the fraction of a chemical substance in the soil that is available for transport, either through leaching into groundwater or through plant uptake. For me, these values are difficult to compare with the Flemish standards. The reasons for this is I'm not familiar with the methodology used to derive these soil standards. It seems that there is no differentiation in land use. What are the background values used? So how do we have to apply these standards? Does it mean when concentrations exceed the total value, remediation is needed? And what about the values applied for the mobile form? The same question as with the former slide. If you have more information about how these standards were derived, how these standards are used, please, I'll be glad that you share your information with all of us. You can do it in the chat or later on by email. And then another important element of the Flemish Soil Decree corresponds to guidelines related to transport and reuse of excavated soil and sediments. This so-called sediments regulation came into force in 2004 to ensure that excavated soil or sediments is reused as much as possible. Within the scope of the reuse soil and sediment quality testing, within the scope of reuse, soil and quality testing must be performed as a function of volume and expected contamination before the transfer of excavated soil or sediments is allowed. Furthermore, specific standards have been derived to prevent soil pollution and to comply with the standstill principle. I didn't add the standards here on slide, but I add at the end of the presentation, you will find references with links to several websites. So depending on the analytical results, batches of excavated soil of sediments and the comparison with the standards receive a 3-digit code, which indicates whether the excavated soils or sediments are suitable for free use, for reuse in construction or infrastructure works, or use in shape retaining products, such as, for instance, bricks, concrete, or tiles. Regarding to these two possible applications, also a leaching test must be carried out to evaluate possible release of contaminants. A certificate will be handed out to confirm the results of the quality assessment and to indicate the possibilities of reuse. So coming back to the standstill principle, this principle essentially means that when excavated soil is reused, the soil quality must not deteriorate in comparison to the current state of the soil at the receiving site. In other words, the reuse of excavated soil must not lead to additional contamination or a worsening of soil conditions at the new location. The standstill principle dictates, in fact, that the quality of the excavated soil must either match or be better than the quality of the soil at the receiving site. For example, if the receiving site is clean or slightly contaminated, it cannot receive a more contaminated soil from another location. The soil brought in must be equal or of higher quality to ensure that there is no net increase in soil contamination. So, and as just said, every batch of excavated soil or sediments receive a 3-digit code that determine the reuse of possibilities. And here I have two examples. 211, a code of 211 means that the excavated soil of sediments can be used freely. So it can be used on other lands It can be used in construction works. It can be used in shapes and so on. A 911 code, however, corresponds to very contaminated soil or sediment, and this soil of sediment or these batches must be transferred to a soil treatment center or even transport at a landfill site. And of course, you have different combinations in between. Okay, that was not all about, because it can be a whole day on itself, the Flemish soil decree, but I hope that I give you some extra insights. I don't know whether there are already questions about this part, which is quite heavy stuff, but
let's give some minutes the floor to the candidates and the trainees to see if there are questions. I know you also post already some questions to them, Ilse, so please fill in the chat or speak up if you have questions or remarks on the first part. I saw in one of your slides, Ilse, indeed on the Ukrainian threshold values, you indicated for one parameter brown and yellow.
Yeah.
I can already tell that it was a language translation issue. It was meant boron. So
okay, yeah, I
so
forgot
that's
to
for you.
ask. Indeed.
Yeah. So this is what it meant. Okay. I don't see any questions popping up, Ilse. So in sake of time, maybe
Okay.
I think it would be good to continue and let's indeed have a look on the European level, what there is related to soil legislation. So thank you.
Okay, thank you, Christophe. I'm moving on. So what about EU legislation? So unlike Flanders, the EU doesn't yet have a legally binding soil directive for soil protection and remediation. The EU soil monitoring law offers only a framework for monitoring and protection. This law was proposed by the European Commission in July of last year, but it has not yet been formally adopted as of date. The proposal is currently undergoing discussions and negotiations among the different EU member states and the European Parliament, which is part of the standard legislative process in the European Union. Once the law is agreed upon by both the European Parliament and the Council of the EU, it will be officially adopted. What are the key aspects of this European soil monitoring law? The first important aspect is the establishment of a comprehensive monitoring framework across the EU to assess soil health. Member states are required to collect and report data on soil conditions covering aspects such as organic matter, contamination levels, and erosions. Soil monitoring law, as the soil monitoring would complement the Water Framework Directive's integrated river basin management by addressing soil issues that directly impact water bodies, leading to more effective, holistic environmental protection. Another important criterion of the European soil monitoring law is the soil health criteria. The legislation introduces a common EU definition on healthy soil and sets criteria that must be met, including limits on pollutants and requirements for organic matter. Furthermore, member states are required to develop and implement soil action plans, addressing issues like degradation, soil sealing, and of course also soil contamination. And these plans must align with the EU's overarching environmental goals. What about sustainable land use? The law promotes sustainable land use practices and aim to limit soil sealing and ensure that degraded land is restored to a healthier state. It furthermore encourages sustainable farming practices, such as crop rotation and reduced use of chemical fertilizers and pesticides to enhance soil fertility. And as in Flanders, a register of contaminated soils will be established. This EU register will contain an overview of all EU sites being identified by the member states as potentially contaminated. And then there is a proposal of the establishment of soil districts. This proposed concept is not officially defined. The concept of the soil districts refers to areas that share common characteristics in terms of soil types, uses, environmental challenges, or management practices. But the definition of soil districts has to be filled in by the member states or even by different regions. The proposition of soil districts aligns with the idea of coordinating soil protection measures across borders and regions with similar conditions. So, although the Flemish Soil Decree and the EU Soil Monitoring Law share common goals in terms of preventing and addressing soil contamination, they differ in their legal frameworks, specific measures, and enforcement approaches. As already explained, the EU doesn't yet have a legal binding soil directive, but the soil monitoring law is intended to complement and reinforce other legal frameworks by introducing consistent EU-wide standards for soil monitoring, assessment, and data sharing. This figure illustrates the main EU directives, like the Water Framework Directive, the main strategies, like, for instance, the EU Soil Strategy and the European Green Deal, and also some guidelines, like, for instance, the guideline on priority substances that are linked or in close connection with the EU soil monitoring law and vice versa. The EU Water Framework Directive and the Soil Environmental Law or the Soil Monitoring Law are closely linked through their shared goals of protecting and improving the environment. Both directives or laws strive to control pollution, to control ecosystem health and sustainable resource management, but with a focus on different environmental matrices like soil and water. Although soil and water are sometimes considered as independent from each other, their health and quality are influenced by each other. So it's important to always keep in mind that soil health is critical for water quality and vice versa. That's already indicated by Jan in his first presentation. Therefore, several EU laws and strategies consider both soil and water as an integrated or in an integrated way. So through all directives illustrated here, the EU has created a comprehensive legislative of legal framework that ensures coordinated action on soil and water conservation, pollution control, sustainable land use across the different member states. This slide illustrates, in fact, a bit more the main principle of the Water Framework Directive. So, and as already discussed by Jan, soil contamination put pressure on several receptors, such as surface water bodies, groundwater depending ecosystems, surface water bodies, wells for human consumptions, and aquatic ecosystems. Following the European Framework Directive, measures should be defined, and actions should be taken to reduce pollution emissions to ground and surface water. So within this respect, monitoring programs must be defined. To estimate the effect of defined measures and to evaluate measures taken, a follow-up is needed of soil, within the Water Framework Directive of groundwater and surface water quality. So, in fact, the soil monitoring law can be seen as a critical missing link to the EU Water Framework Directive and other environmental regulations to improve environmental ecosystem services. So that was a bit a shorter part. I don't know if there are questions here about the EU law. Otherwise, I think we just had a small break that I can proceed. Is that okay, Christophe?
Yeah, that's good. Let's see if any questions are popping up. It was good indeed to have the link to the legal European law that is coming up. Also, because as you will see later on, when we will discuss the analytical methods, also we will consider the European methods, because the legislation is strongly bound to the methods, so they propose methods. So we will also consider that in the modules thereafter. I don't see any questions at the moment, Ilse. So I think it's now then good to go to the next part related to the basic principles of human risk evaluation.
Okay, thank you. So the EU soil monitoring law, by ensuring health and sustainability of soil ecosystems, it plays a crucial role in safeguarding human health, as soil quality directly affects food safety, water purity, and exposure to harmful pollutants, factors that are fundamental in any comprehensive human risk assessment. Although human risk assessment, you can also talk much more about it, but I will only give the basic principles in this part. But at first, the research flow of the contaminant soil investigation in Flanders is given. In fact, it all starts with the question, how do pollutants end up in the environment? Pollutants enters the environment through various pathways, broadly classified as diffuse sources and point sources. So these two concepts are crucial in understanding how environmental pollution occurs, especially in conflict zones like the war in your country, where both types of pollutions will occur due to the disruption of infrastructure, industrial activities, and military actions. Diffuse pollution, also called non-point source pollution or regional pollution, refers to pollution that comes from multiple widespread sources, making it harder to pinpoint the exact origin. This type of pollution often results from activities spread across large areas, such as agriculture and urban settlements. Sources of this pollution are airborne pollution, as for instance from bombing and explosion. So when bombs or missiles are detonated, they release toxic chemicals and particulate matter into the atmosphere, which can later settle on the ground or on water bodies as fallout. In urban areas, as indicated in this figure, also the destruction of buildings may release asbestos, heavy metals, and toxic dust into the air, affecting large areas. Diffuse pollution in conflict zones is widespread and hard to control, as it affects large areas and is often the result of multiple scale sources, including, as already said, the impact of military activities, the destruction of land, and also the absence of environmental management practices. Point source pollution refers to pollution that comes from a single location. Examples are direct impacts from localized attacks to specific sources like factories, industrial plants, wastewater facilities, or, for instance, pipelines. Point source pollution in your country can cause localized but severe contamination around these facilities, which can be long-lasting and difficult to remediate. So this figure gave a nice overview, and thanks to Gilles for it, a nice overview of the framework and the different parts of contaminated site research in Flanders and Wallonia, but it accounts also for the approach of other countries as well. So in several countries, soil research start in general with a preliminary or an orientation study. Depending on the outcome, a more detailed characterization study, and I already mentioned it before, descriptive soil research has to be carried out. And it's within the framework of the descriptive soil research, a thorough risk analysis is needed to evaluate the need of remedial actions. Going a bit more in detail, here you can see the research flow of soil and groundwater investigations as an example of Flanders. So preliminary soil research assess whether a contamination may be present or not. The main purpose here is to verify whether there is a clear indication of a serious threat to humans and the environment. In general, a preliminary soil investigation consists of an in-depth historical research of activities taking place at the site to be studied. With respect to a preliminary soil research, also a limited monitoring will be carried out. In Flanders, preliminary soil research have been carried out periodically in function of the type of activities taking place on different sites, or when risk activities are closed, or in case of the transfer of land. As said, when a preliminary soil research indicates a possible risk, then a descriptive soil research has to be carried out. A descriptive soil research is not necessarily conducted for the complete research site, but only for those zones and parameters for which threshold values are exceeded, or for which the preliminary zone investigation indicated a possible risks. A descriptive soil research includes the determination of contaminant mass, which is, as Jan indicated, very important within respect to eventually remediation actions, the delineation of the pollution, risk assessment, and the need of the evaluation of the need for remediation. And as said earlier, soil remediation in Flanders must be carried out for historical contamination when there are indications of a risk to remove the risk. For new contaminations, immediate actions are needed immediately, needed immediately, and remediation have to be according to the guiding values. So here again, I can ask questions to you. I don't think that we can copy paste of this workflow that it's recommended to your country. You know that there were indications for severe contamination. So I don't know whether there is still a need of preliminary soil research. I don't think that the complete workflow can be applied, but probably the possibility of combining both types of soil research can be recommended. Post-war research is essential to address the environmental impacts of the conflict, to assess soil contamination, and to restore agriculture and industrial land. And because of the extensive destruction, the presence of various pollutants there need for a pragmatic approach which focus on high risk areas, on black spots, the identification of contaminants and soil disturbance, rapid screening, which is already going on, as illustrated by Nathan on Tuesday. But also here, a risk-based remediation is very important in combination with a long-term monitoring. So these are actions that we have uptaken in a indicative or preliminary soil research, but there is a problem already, so you can start with it as the first phase, for instance, of a descriptive soil research. So, but I already mentioned that a local or that a specific risk assessment is an important element in the execution of soil survey. So, and it comprises human risk assessment, ecotoxical risk assessment, and the assessment of spreading risk, like leaching, the movement of groundwater plume, and movement of pure product. Ecotoxical risk assessment is not covered in this e-learning project. The determination of spreading risk, I already indicated that it will be tackled in the session, I think, of tomorrow morning, I'm not sure, by Ingeborg Joris and Jeff Dams. So, and as indicated on this figure, I'm not going in detail, but part of the elements or of the specific risk assessment will also be tackled in other modules as well. Why do we need to carry out a location-specific risk assessment? I will summarize it a bit. In Flanders, we need it to determine whether there is a serious soil contamination in case of a mixed, predominantly historical contamination, or whether there is a risk for parameters for which no remediation values could be derived. I also said that when there is a new soil contamination, that remediation is needed immediately. But sometimes, due to technical and/or financial reasons, this is not feasible. Also, in that case, a thorough location-specific risk assessment has to be carried out. Besides the evaluation for the need of remediation and the priority of the remediation, a risk assessment also have to indicate whether there is a need for safety measures and precaution, or for the formulation of recommendations. So the next slide I will skip. You can read it afterwards. It just indicates the difference between safety measures, precautions, and the recommendation for use. So now I come to the start of not only a human risk assessment, but in fact, Jan indicated it already, a conceptual site model is very important with the executing of soil and groundwater investigations. But also for the risk assessment, the actual and the potential risk evaluation start by completing the conceptual site model and the source path receptor analysis. Completing, so from the moment you have extra information, you always have to add it to the conceptual site model, and then afterwards you can going on with the risk assessment. So at first you determine, or you have to determine, the current or the actual risk of the contamination. And this actual risk you have to evaluate as a function of the use of the field site, the typology of the site, and here it's meant land use, the land use, so nature, agriculture, residential area, and so on. Also, the characteristics of the site. Is it an industrial site? What activities are taking place on the site? Are the storage tanks, and so on? What's the contact between how long are people on the site, and so on? All these elements you have to take into account to draft the human health risk assessment. These actions you have to do for the actual risk, but of course you also have to evaluate the presence of potential risks. So the potential risk is based on the potential future contamination situation as a function of likely or real future changes in use and also potential changes and so on. So the same parameters that you have to apply for the actual risk assessment, you also have to take in account for the potential risk assessment. Besides information on the source, you also have to indicate the path of the pollution and the receptors. Who is exposed? What are the subpopulations? And is the exposure only taking place right now, or is it only possible in future? So then it's very important to identify the exposure routes when carrying out human risk evaluations. Exposure routes refers to the ways by which humans can encounter environmental contaminants. So these exposure routes are essential for understanding how harmful substances enters the body, which influences on the furthermore the assessment of potential health risks. What are the primary exposure routes that can be identified? That's the oral uptake of, for instance, contaminated food, water, soil, or dust. Also, accidental ingestion have to be taken into account through occupational settings or through hand-to-mouth activities, especially, for instance, children playing in the garden. Another important exposure route is inhalation by breathing in airborne contaminants, such as gases, vapors, aerosols, or particulates, such as dust, fumes, or smoke. Common sources for airborne contaminants are industrial emissions, vehicles exhaust, indoor air pollution, or contaminated air in the occupational settings. And the third important exposure route is through dermal contact, contact of the skin with contaminated sediments or water. And then a minor route, which is not indicated on these figures, is ocular or eye contact with hazardous substances. So typically for the site you are investigating, you have to determine which is a typology of the site and which will be the typology of the site in future for the potential human risk analysis. And for each of these typologies, you have to draft scenario analysis and you have to indicate which of the exposure routes are or may be applicable. So then you have the conceptual site model. You have in between the identification of the exposure routes, and you have carried out scenario analysis. The next step is to calculate the human risks using an exposure model, such as, for instance, S-risks. Other exposure models are on the market as well, and it's important when you select a model that is appropriate for the type of exposure being evaluated. Due to scientific evolutions, it's recommended that you use a computational model to which you can add soil layers at variable depths, in which you can enter established groundwater table, pollutants, different pollutant matrices, concentrations, and so on. So in fact, you have to choose a model to calculate human risks that can take into account specific site characteristics. This, based on the site characteristics you give in, this model will calculate the risks according to the given input and will indicate whether remediation is needed or not. But as for every modeling exercise, be always critical when evaluating the outcome of the risk model. If you have the possibilities to fine-tune the model, please go ahead. So include chemical analysis for different soil horizons, take groundwater samples at different depths, and for instance, include other measurements like soil vapor measurements, concentrations of drinking water analysis, and so on. This will help you to adapt the human risk evaluation to location specific situation. And then something specific for Belgium. I don't know whether this exists in other countries. There are policy adjustments with respect to remediation obligations. So in some cases, regardless to the outcome of risk analysis, for some specific parameters observed, a policy value for soil has been derived within the Flemish regulation. And these values have been developed according to the prohibition to leave waste behind, where, in this case, very high concentrations of contaminants are considered as waste. So when one of the contaminants indicated here exceeds, when the concentration of these contaminants exceeds the policy values, then you don't have to carry out a risk assessment. You can immediately go to drafting the remediation plan. The same counts for LNAPL and DNAPL, which when there is an indication that a pure product is present, then there is no need in carry out a risk assessment. Then you have to go immediately over to take remediation actions. So these are policy values set for soil. The same counts for groundwater. So regarding groundwater pollution, policy adjustments of remediation obligations are given for the chlorinated aliphatic hydrocarbons. So, and the policy values are set or related to 1 or 10% of the solubility, depending on the type of pollutant. And when you encounter in your groundwater results concentrations exceeding these policy values, also in this case, no risk assessment is needed, and you have to go immediately to draft a remedial action plan. These are policy values when you encounter very high concentrations, but also for some organic substances, such as, for instance, benzene, 1.2 dichloroethane, vinyl chloride, chloroform, and so on. It's possible that even at concentrations below or very close to the limit of quantification, or very close to the target values, which normally does not indicate a risk, that when carrying out the risk assessment, that a human toxicological risk is indicated. But in fact, for these substances, is accepted that there is no serious soil contaminated expected when you have or you observe only concentrations below the soil remediation standards, or when the concentrations observed for non-standardized parameters are 5 times below, or are below 5 times the limit of quantification. So in these 3 cases, you don't have to carry out a risk assessment. In the first 2, you immediately have to go to draft a remediation plan. In this case, you don't have to take any further actions. So to summarize, in this session, we have explored the Flemish legal soil framework to illustrate the general framework for contaminated soil research. This framework ensures that contamination is systematically addressed and aligned with sustainable development goals, focusing on remediation and prevention. Specific attention was given to the determination of threshold values, the soil settlement regulation, and human risk assessment. It was further illustrated that the proposed EU soil monitoring laws goes together with other EU legislations and strategies, like, for instance, the Water Framework Directive, to create a regulatory environment that promotes a holistic environmental protection. The growing recognition of soil as a crucial component of ecosystem health reinforces the need for stronger EU-wide soil protective measures. And then some closing thoughts about the post-war research in your country. So in your country, the contamination from the military conflict induced complex challenges that require a tailored approach for soil contaminant research and risk assessment. So you have to ensure land use, protecting human health, and restoring ecosystems will be essential in the Ukraine's environmental recovery. Therefore, a robust legal framework, a comprehensive monitoring and risk assessment strategies are essential for sustainable development. And in fact, the first step is already taken with respect to the resolution adopted recently. So moving forward, the ongoing harmonization of soil and water protection across the EU, coupled with effective post-war environmental management strategies, will be fundamental to address both legal and practical challenges. So thank you very much. I don't know, I see some questions in the chat. Nathan, yeah, you have the question, what type of pollution is worse, point source or diffuse? Yeah, that's a I said something about it, but it's indeed a difficult question. Diffuse pollution is covering broad surfaces, impacting many people. In general, the concentrations are not that high as concentrations encounter with point source pollution. But okay, point source pollution, you can locally have very, very high concentrations, but it's possible that the effect to the surroundings is more limited. So, okay, yeah. I agree that it's difficult to answer or to say diffuse pollution is worse compared to point source pollution or vice versa.
Okay. Thank you, Ilse. Thank you very much for the presentation. I think indeed the question of Nathan was also to trigger all the candidates, so not especially for you. And I saw they were answering very well. I think, Nathan, you raised your hand, so maybe you have some other comments or suggestions at this point.
Yeah, I just had an interesting question. So in Belgium, the priority is risk assessment and then remediation to numerical standards, if I understand correctly.
For historical contamination. So for contamination occurring before October 95. Yeah.
Interesting. That's interesting. So in Canada, you'll find that people's priority is numerical, remediating to numerical standards. So quite often you'll remediate will be the first option. And then if remediation isn't feasible or it's too expensive or technically not able, then you'll switch to risk assessment. It's just interesting. I imagine that might have something to do with the size of our countries. I suspect we have a lot of landfills and landfill capacity, and the priority is then just to dig everything out and get rid of it. But maybe, I don't know, maybe you can comment on that or have some thoughts.
Yeah, but if in the region where the landfill, for instance, occur, when there is no risk or when there are no nearby receptors, then that money can be used for a location where the risk is higher and where there is a more urgent need for carrying out the remediation.
Yeah, that seems like a better system because I've done quite a few projects where we haul, thousands of cubic meters of soil and just put it in a landfill and then haul in new soil where maybe all the other externalities as far as like sustainability or carbon emissions or road accidents aren't really factored into the whole, the big picture of the project. So that's interesting.
Okay, are there any other comments or questions? Otherwise, I think our next speaker will be Wart.
Sorry, there was one other comment on the diffuse pollution.
Yeah, I think that was an answer to Nathan's question.
Okay.
Ilse, just for me, the pictures you saw on your previous slides, are they like from Belgium, from the restored war zones, I guess?
No, they are. It's in. Yeah, I don't know if you can read it. It's from the Valley of the Somme in France.
Okay. All right.
So
yeah.
it's the battlefield of
the Second
World War. No, it's the First World War,
one,
I guess.
Yeah,
it's the First World, but it's the Valley of the Somme. Yeah.
Okay. No. Okay. Thank you. All right. If there are no questions, I propose that we continue with the last part of the morning session. I think our next presenter will be Wart.
Yes, indeed.
Hello. Good morning, Wart.
Just a short question. Is there a small break, or do I just continue right now?
Maybe just a small break, because I think it's time now. Let's give it 5 minutes so that you can meanwhile share your presentation, looks if everything works well, and give the people the opportunity to get a coffee or use the restroom. So let's say 5 minutes from here. Yeah, Wart, if you can meanwhile share and then check if your laser pointer is doing well. We still see, I think, Ilse's screen. Oh, no. Wart's Winnen is operating. Yeah. Perfect. Yeah. We see now your presentation mode already. Yeah. That seems to work as well, Wart. So yeah, looks good. I think we are a little bit ahead on the time schedule, Wart. But it's important that you speak slowly and articulate well in order to give the translator the opportunity to translate well. So I will not urge you to speak fast, but yeah, we'll see how where we end. At least you're the last presentation for this morning.
Yeah, no problem.
All right. I don't want to keep you waiting any longer, Wart, for your presentation.
Okay.
So I think after the general concepts of soil and groundwater presented by Jan, and thereafter the legal frameworks existing presented by Ilse, it's now time for a third topic, the data handling, all meant to give you a very global and general view of the basic principles on how to deal with soil contamination and groundwater contamination. So Wart, please, the floor is yours. You can start with your presentation.
Okay, thank you. My name is Wart Swinne, working also at Vito, the same team as Jan and Ilse, the two previous presenters. And my presentation will be about data handling, how to deal with all the data coming from your soil research, pollution research, groundwater research. And the presentation is relatively broad. I have avoided to give examples which are too precise, but I have added some examples just to show what you can do with certain techniques or with certain ways of dealing with data. So in this presentation, we will give a broad overview of what different data can come from different data collection techniques, how we can structure them, how we can work with them, and how we can use them to form the basis of good soil and groundwater research and also good decision making coming from those data. Sometimes it's a bit tricky to work with data in an environmental context, and that's because by nature, the environment is quite diverse, and also the data coming from soil and groundwater research can be quite variable, and it's sometimes tricky or difficult to deal with that and to make use of that diversity in a good way. And next to that diversity of data in recent years, also the simple quantity and availability of data is increasing a lot. Many examples can be given. For example, laboratory techniques can now use non-target techniques, which not only give you, for example, the concentration of a single or a few chemicals, but can give you a very broad interpretation of maybe hundreds or thousands of different molecules being present in your sample. For another example is, for example, remote sensing, where satellites can measure enormous amounts of data of your land surface, which all can be incorporated in your project. And so it requires more and more special attention to deal with data properly. So the focus of this lecture is two parts, basically. One is an overview of data collection. What are different data types? What challenges are related to those different types? And what are some basic principles of good data management that you can use in any study to properly collect and organize your data? And then the second part is more applied. Once your data is properly structured, how can you use it to support your research and answer the questions you have? That can be with statistical evaluation, that can be with modeling, for example, process-based modeling, think of a groundwater model. And here I added some examples, mostly from Flanders, just to give some indication of what is possible or what are the up and the downsides of some techniques. Just an overview of some data types that are very relevant in soil and groundwater research. One is field data. I think many studies rely a lot on field observations. This can be both simple observations of local conditions and can also be samples of different environmental media such as soil, groundwater, sediments, air, even sometimes. The upside is that they provide a good snapshot of a condition at a certain location and can be analyzed very precisely. But the problem is that it can be heavily affected by local conditions. Where do you take your sample? At what depth? At what location? Human error in sample collection. And also it has to account for the environmental variability that is present. Another downside is that it's often quite expensive and time consuming to collect a proper data set like this. Remote sensing is something that is also being added more and more in environmental studies, not always in a pollution context, but at least it provides good background data for your environmental situation. The advantage is that it provides a lot of information over large areas and sometimes even with a good temporal resolution, so with several images in a short time span. Problem is that sometimes the resolution is limited and the connection between the measured data and, for example, the situation on the ground is not always so simple. And sometimes it requires additional ground truthing or validation. Then laboratory data, also one of the most important groups in pollution studies. The big advantage, of course, is that you get very specific information with often very accurate results, with the downside that it can be costly to have very precise results, and you often need quite some equipment to perform these analyses. And next to that, of course, you can do several measurements, but to, for example, situate your study in national frameworks or international frameworks, often specific protocols need to be followed, each also with its own requirements. And then a final group that's also very relevant for pollution studies is, of course, modeling data. The advantage of modeling is, of course, that you can go beyond what you observe. You can predict future trends. You can test different scenarios, sometimes even which do not necessarily correspond with reality, but it can give you a lot of additional insight without needing extensive fieldwork. One of the challenges, of course, is that the model is only as good as the data or the assumptions or the equations that are present in the model. And also here, proper calibration and validation is needed. And of course, next to these four categories, other data sources can be thought of. Actually, any kind of information that can help you understand, for example, your local pollution context. Think about newspaper articles, historical research, previous reports. All those things can, of course, help and do not necessarily fall in these categories. If we think of all the data that's collected in a study or a pollution study, we can broadly group them in two categories. First of all, the qualitative data, which are not numerical, so they don't give you a value or a number, but they describe certain characteristics or some attributes of your local situation or of your case. The upside is that they provide a lot of context for interpreting any quantitative data that you collect and can also help a lot in decision making. The problem here is that those data are sometimes a bit subjective and are quite difficult to compare across space and time. Those things are much easier and more clear with quantitative data, which are numeric data measuring specific variables. Think of modeling results, think of lab measurements, think of remote sensing results. And they form the basis of further analysis, either statistical or in modeling. The advantage is also that you can use it in a very objective way, for example, comparing it to pollution thresholds. The few challenges that are linked to quantitative data are, of course, the precision and the accuracy of the obtained results, and that to obtain good quantitative data or representative quantitative data in all the different steps of the data collection, attention to detail has to be paid. What are common data challenges in pollution studies is, of course, something I mentioned earlier, the complexity of environmental systems. You're dealing with different media, but also different spatial structures, be it parcels, be it regions, be it different elements of the biosystem. And so you need accurate and good data collection to represent that variability also in your data set. That means that you need to cover the different spatial components, but sometimes also different temporal components. For example, if you think of a pollution plume that is traveling in, for example, groundwater. Another data challenge is, of course, combining different sources, each source having its own quality, having its own precision, having its own format, and different ways to use it, and combining that in a single database or in a set of data which you use to build upon for your study. That's sometimes tricky. A good way to deal with different data sources is to keep yourself as much as possible to standardized processes, standardized protocols, which first of all avoid errors, but also provide you with analytical rigor. And then a few challenges that are common in almost any data source is inconsistencies, for example, between measurements or between different data sources. Incompleteness, any data set can have its own missing values or missing measurements. And of course, uncertainty, which is worse for some data sources than others, but the variability that is present in the measurements and in the conditions in which your measurement is done eventually also leads to uncertainty in your data set. And of course, in an ideal world, that uncertainty is as low as possible. So there are a few main principles of data management that you can use to avoid these challenges as much as possible. And the first one starts with the data collection. And these principles are not linked to specific categories of data. Actually, they are applicable to any kind of data. First of all, one of the basic principles is that you do a systematic data collection as much as possible. So preferably your data collection is done in a standardized way, and errors are avoided as much as possible by that, which can eventually compromise later analysis. The focus should lie on accuracy and reliability of your measurements, reproducibility, so that also means, for example, taking a double sample in the field to do extra measurements afterwards, or also following exact procedures that someone else can actually control or read how the sample was collected. That also leads to an efficient sampling campaign or efficient data collection. Good practices here are standardization of your data collection, calibration of your instruments to avoid instrument error, and good field logs and notes so that you have a documentation of how the samples were collected. Once you have your data collected, the second step is that you do a data quality control and a validation of data that you collected. You can do both quality assurance and quality control. So quality assurance is actually the set of processes, of protocols, of guidelines that are present to ensure that data collection and also the further use is done in a rigorous way and also in a way that can be repeated also by somebody else, for example. So that involves actually all the planning that ensures that your data is qualitative from start to end. Then a step further is quality control, where next to trusting on your processes and your protocols, you also go back to your data once they are collected to hands-on check if they are correct, if there is maybe any additional validation, any additional cleaning, or any additional step necessary to ensure the quality of your data set. This can involve outlier detection, detection of missing data, for example, a sensor that was offline for a certain period of time, maybe detect if there are some duplicate data present in the data set that should not be there. So that's the second and more hands-on way, and also that's well, that's to be advised for any data set you use in further research to avoid problems afterwards. Once you have your data collected and you also have them checked or double-checked in terms of quality, it's time to organize and storage them in a good way. You can use different data formats depending on the type of data you have. You can use spreadsheets like Microsoft Excel. Sometimes it is seen as maybe an amateur way of working with data, but actually for many applications, a simple Excel spreadsheet can already bring you very far, and it's maybe used more often than you sometimes think. Of course, if you have very large data sets or complex relational data or environmental data, an Excel sheet or a spreadsheet will not be enough. And then you can move to more sophisticated database systems that also make it easier to query your data or to use it in a more complex way afterwards. Of course, if you have spatial data, you can also use GIS systems that are specifically designed to work with spatial data, coordinates, and maps, for example. Here you can pay attention to organize your way in a good, well, to organize your data in a good way, to work with different versions of your data set to avoid confusion, to work with consistent naming. For example, if you work with measurements of chemicals, a chemical can have very different names in different languages. You can also type it in different ways. But for example, almost any chemical ingredient has a CAS number, which is a unique number for that active substance. And if you work with that code instead of the name, for example, you avoid a lot of confusion and maybe some human error afterwards. And also organize your data in a hierarchical structure to make sure that you can have a broad overview if you want, and you can have a detailed overview of some subparts of your data set if necessary. If you store your data, of course, you should also consider the problem that your data could get lost by deleting them yourself accidentally, or for example, by an IT system crashing. So also think about your backups, storing it in the cloud, or any more advanced data retention policies. Maybe less interesting, but still very important part of data management is having good metadata. So metadata is actually, if you read it literally, it's data about data. So if you collect data from different sources, if you put them together in a database, if you do some quality checks, all those steps should be described, documented. What are the properties of my data? What is their resolution? What is when were they collected? What timing was there in that data flow? All of those descriptions, all of that information should be stored separately in what is called the metadata, and it contains, yeah, like I said here, different components: the source information, the methods, the units. Is it spatial data? If so, for example, what coordinate system are we working in? And that also ensures that your data is reproducible. So someone else doing the same procedure should come up with more or less the same results. It can help in collaboration. For example, someone else who was not involved in the project from the start can still trace back what was done in detail. And it also ensures long-term use of your data. If your data set is reused after several years, that also all the details are still present and available for anybody who needs them. Here you can also think about maybe data security practices or sensitivity because sometimes, for example, pollution data can be sensitive data. So here you can think of access control, encryption, regulatory compliance as well. And all those things can also be described in the metadata. Then we move to the second part of the presentation. So once you have your data collected, properly organized, and set up in a data set, it's time to start working with it. And the first step, and maybe the easiest, but also one of the most important steps, is that you do an exploratory analysis, so that you take your data set as it is and just look at the main characteristics. That can be done visually, for example, making a small map of data, if it's spatial data, making a simple histogram or a box plot or a scatter plot of the data that were collected, just to see what's in there. Time series plots can be done if it's temporal data, and you can use for those techniques very simple descriptive statistics. What are my mean values? What is my variability that's present in the data set? Just to have a broad idea of what is there. Then, of course, further statistical analysis can provide you with more insights, especially in understanding the relationships that are present within the data set. And of course, a variety of statistical techniques is available, each with its own strengths and weaknesses. And actually, the choice of technique depends a lot of how much data you have, how robust can you make a certain statistical technique, what data types do I have, and what questions do I have relating to those data. And so each technique is often linked to a certain type of research hypothesis. Am I interested in trends? Then I go to a certain type of analysis. Am I more interested in outliers? Then I go to another type of technique. And so actually it's the research hypothesis and the type of data that's present that determine which technique is best suited. A note here is that more complex techniques are not necessarily always better, as they often come with their own risks and limitations. So sometimes a simple technique, but with a robust execution and with enough data, can be a better option than going for a complex model if you, for example, don't have the amount of data to back it up. Something that will also come back further in the presentation when we're talking about models. I listed here the usual suspects of statistical analysis, and I gave a simple, quick description of what can be done here. I won't explain them all in detail, but yeah, as basic statistical techniques, you can do correlation analysis to see how different variables relate to each other, regression modeling, either linear or multiple, to see how a certain variable changes when other variables change. Of course, time series analysis, if the temporal component is very important. Geostatistical techniques, if the spatial component is important. And all these techniques always, to a certain extent, rely on hypothesis testing, but you also have certain techniques to specifically focus on testing whether certain hypotheses are true or not. Think about t-tests or ANOVA analysis, for example. Here I added 3 examples of statistical techniques that we used in pollution studies in Flanders or in environmental studies, going from very simple to more complex. And it's not a full overview, of course, but it's just to demonstrate in what contexts they were used and how they can provide added value. The first example is chemical fingerprinting. So some pollution parameters, in this case it's PFAS data, are very diverse. So you have multiple tens, hundreds, sometimes even thousands of different chemical molecules that all fall under the same family. If they are all measured, you get a very diverse and a very data-rich data set, which can provide you a lot of information, but which can also be difficult to interpret. So what we did in a few cases was we tried to construct fingerprints. So we grouped the measured data of those PFAS measurements in different families. And here we did that for different samples taken in different locations. And the idea was, can we have a simple technique to see if the PFAS concentrations in certain locations match or not? With the idea that if they would have a very similar fingerprint or very similar PFAS combination, that it could possibly indicate that it's originating from the same source. And so here, for example, below are two radar plots. On the left, you have two samples which show almost no correspondence in their PFAS concentrations or in their PFAS fingerprint. And on the right, you have two samples coming from different locations that have very similar fingerprints. Here, actually, no real statistics or statistical modeling was used. This was just calculating mean values for different families of PFAS. So it's actually just using, well, calculating the average concentration for different groups of variables, nothing more than that, and then presenting it in a visual way. More complex example was where we used the cluster analysis. Here we had also PFAS measurements for a whole lot of sites across Flanders, several hundreds. And we wanted to group those sites in different clusters to see which locations had similar PFAS fingerprints. So on the left bottom, you see the result of that clustering analysis where different groups of locations come up. And based on those different clusters, those different groups, we could also see if there were common properties for those locations. Do they all share, for example, the same industrial activity? Do they share the same spatial location? And we could also see if different clusters were related to certain typical PFAS compounds that would allow us to, for example, identify specific indicator compounds for those different clusters. This was now done for PFAS data, but actually it can be done for any numerical variable as long as there's some diversity present in the data set. Second example is spatial interpolation. So often you do a lot of measurements, for example, soil measurements or groundwater wells, and you end up with a map of different concentrations spread across the landscape, but you actually need also information in between those points. And so you want to interpolate in between those measured points, and you want to come up with an area-wide map of, for example, concentration. On the right, I added a picture of an agricultural landscape. Imagine that you have to sample it. Of course, you're not sampling every square meter of it. And so you end up probably with a map with concentrations looking like the one here at the bottom. I explicitly did not add the parameter that was measured here because actually it can be applied to any pollution parameter that you measure. What we did then is, and it's just to show how it can be used and what some of the difficulties can be. Here we used that data set on the left bottom, and we used four commonly used interpolation techniques. One is not necessarily more correct than the other. Those are often used in many pollution studies and spatial analyses, but you can quickly see that the patterns are not necessarily the same. And the idea is then which is more applicable than the other. And so here, of course, those techniques can be very strong. You can get a lot of added value out of it, of course, based on the assumption that you chose the right technique or the most appropriate technique. And to give you an example, I just took two small snapshots out of that map that you saw on the previous slide. And I will explain the slide a bit to make it a bit more clear. The two left panels are from a location where the concentrations show a very gradual change over space. So where the concentrations show a rather diffuse pattern of pollution. The two panels on the right show a location where there is a very clear hotspot of pollution. In this case, it was from a specific site where pollution was produced. And you can also see it back in the different patterns that there is one location popping up quite a lot. Then we used inverse distance weighting, which is a very common technique for spatial interpolation, but we used different parameter values for that technique. In this case, it's the P value or the power value that's often varied. And actually also here in literature, one value is not necessarily given as being better than the other. It really depends on the application. What you then see is if you use a low power value, which in this case means that points which are lying a bit further away also still have an influence on the interpolated value. It works very well for the diffuse pattern, where you see that you get a nice, well, slowly changing concentration profile between the points. While for the hotspot pattern, what we see is of course, a high concentration being interpolated close around the hotspot measurement. But then we see the values dropping to the next point, but then afterwards they go up again. And that is because points lying further away have a large influence. So you can see that the hotspot pattern has a large area popping up. If we use a much higher power value where only the real local values are important, we can see that the hotspot pattern is well represented. So there's clearly one small location popping up as a high concentration area. While for the diffuse pattern, there we see then that patchy pattern where concentrations go up and down. So if we try to find the best technique or the optimal technique to represent the pattern that's present in the data, we come up with different techniques for different types of pollution in this case. So this just to illustrate that using a statistical technique also requires some insight in how that technique works, and that choosing the right technique and the right way of applying it can really change the results coming out of it. Final example.
Bart, yeah. If I can quickly interrupt, because there was a question on this spatial interpolation. Yeah. The question is, and I think it's your previous slide, yeah, I think you triggered it a little bit. The question is, what type of spatial interpolation is better in soil modeling? And then the question is it like spline interpolation or kriging? So I think it's on the previous slide where can you comment on that?
Yes, indeed. Actually, it depends highly on not only what type of pattern you have, diffuse or more a hotspot pattern. For example, splines have the tendency to really form a smooth surface, as you can also see in the map. That's if you have enough data, if they are properly spaced, and if it's a very diffuse pattern, that technique is perfectly fine. If you have a pattern that's really patchy and that goes from very high to very low concentrations over very short distances, and you have sometimes maybe some holes in your data set, think of some areas where you couldn't measure, for example, then maybe other techniques are better suited. So it's really a bit trial and error. The advantage of kriging, for example, is that it takes spatial autocorrelation into account. So statistically, that's, let's say, the more advanced technique. But it really depends on the data you have. And yeah, I would advise trial and error.
Okay, thank you. Please proceed.
Interrupt me if there's a question, because I can only see my slides at the moment, so I can't see raised hands. So a final example for statistical analysis in this case is a more advanced technique. It's called digital soil mapping. And it's a very useful technique if you have all the data for it. And what it actually does is it also translates data points or point observations to area-wide maps, but it can include any map information or any environmental information that you have available. So the example given here is for Flanders, where we had a lot of soil observations present in a database. Yeah, sorry. So digital soil mapping actually uses what's called the Skorpan paradigm. It's not that important here, but what it actually does is it takes a certain soil property, which you want to predict or you want to model on an area-wide map, and it links that property to different other variables that can explain the pattern of that soil property. Think of soil type, think of climate, think of topography. But for example, you could also think of industrial activities, think of land use planning, and so on. And what it actually does is it takes all the data points you have, so point observations of that soil property, and then you provide a lot of maps to that model, maps of topography, maps of the soil type, maps of industrial activities. And for all those point locations, a certain statistical model will look for statistical relationships between those mapped variables and your point data. And then for each location in the area you want to model, it will then predict that soil property based on those statistical relationships. So you model that soil property also in between the points you measured. In this case, for this study, we tried to model where in Flanders organic soils were present. So peat soils, organic soils was the soil property we measured and we wanted to model. And then we provided in total 83 maps of different environmental predictors that we thought could be linked with that soil property. And in this case, we used random forest techniques to come up with these statistical relationships. And what you then end up with is a map, in this case, a probability map, where between 0 and 100%, the model would predict whether organic soils would be present, yes or no. It's a complex technique because it requires a lot of data points, but also a lot of maps of the different properties that might be linked to, for example, organic soils in this case. But if you have the data, if you have the maps, it is a very strong technique to come up with maps of certain soil properties. And actually, the type of soil property you want to predict doesn't really matter as long as you have the available information, so both the point measurements and the maps that can be linked to it. Then a final part I want to discuss is process-based modeling. So the previous slides were all on statistical techniques. But of course, in pollution studies, you can also use process-based models. Think of groundwater flow models or even contaminant transport models that also simulate the spread of contaminants in the subsoil or in the groundwater. The big advantage of these techniques is that it really provides a mechanistic understanding of what is happening with your contaminant or with, for example, your groundwater. And it also can predict future situations, both in space and time. And so it's very complementary to statistical modeling because it tells us what is happening, but also why it is happening, which is not always the case with statistical techniques. Downside, of course, is that you need a lot of calibration and validation and a lot of data to come up with a proper process-based model. In calibration, you adjust the model parameters to match observed data from the field. So you use measurements, real-life measurements from the field to check if the behavior that is present in the model corresponds with reality. Once that is done and you have your model set up, You do also a validation step where you check afterwards your calculations of your model with, again, a data set, preferably a data set that is not used in the calibration step, to see if the predictions that come out of the model match reality as well. You can also complement it with an uncertainty analysis. You have a lot of different variables, a lot of different processes present in your model. Some might be very important and very sensitive, others might not be. And knowing which of those processes and which of those characteristics are very influential is very useful information. And an example is given here below, where you, for example, if you find out that your model is very sensitive to assumptions about, for example, hydraulic properties of the subsoil, you can, for example, do additional tests or gather additional data to better constrain that parameter. A more complex model is not always the best. I added this graph here to illustrate it. On the y-axis, you have the error, and on the x-axis, you have model complexity. So if you have a very simple model, then your data required to get that model running will be simple and will be not that difficult. And so your input error will be small. But on the other hand, the model is very simplistic, so probably the error created by the model itself, because of its generalizations and assumptions, will probably be high. The opposite is true for a very complex model. It will be very precise and correct in its calculations, but it has a lot of data requirements, a lot of assumptions, and if those data requirements and assumptions are not all properly constrained, you can have a lot of input error. So a lot of error originating from the data you need to feed the model. And so the optimal is somewhere in between. And actually this optimal location can shift depending on how much data you have available to calibrate your model, how much data you have to feed your model as input data. It can be dependent on the type of environmental medium you're looking at. For example, a groundwater body can be different in its data requirements than, for example, modeling soil or modeling air, for example. And then a final step after your analysis is, of course, a communication of results, because an effective communication of your research results bridges the gap between what you do as a scientist, measuring and analyzing a certain case, but also the policy and possible actions coming out of it. So there, of course, you need to tailor your communication to your audience. Is it a scientific audience or more a civilian audience? You need to clarify certain complex results if necessary, or maybe even simplify it, although that's always a bit tricky to avoid oversimplification. Use visual tools if possible to communicate it in a more effective way. And of course, be transparent about the limitations of your research, acknowledge certain uncertainties or data gaps, and present maybe actionable insights. So if you present your data, make sure that the insights that come out of your research, that there are certain actions can be linked to those, to avoid that your results are just being the results and no follow-up or no actions are coming out of it. And if done well, end products can be both a scientific tool and a communication tool. I have an example of that as a final slide. This is, for example, something we made at Vito about heavy metal concentrations in groundwater. It's an online web tool that is used by professionals to assess the heavy metal concentrations in a certain area in the Campine region in the groundwater. And they use it if they have, for example, a project or a study going on in that region, and they want to check the regional situation at their location. So it evaluates the need of remedial action. It's also used for reporting, but it also provides the results in a very clear way. There are maps included, there are time series included. you can click on certain locations which you are interested in. So if done well, certain tools can serve different purposes and can even serve different audiences, going from scientific to political to professional to even civilian. That was my final slide. If there are any questions, I'm happy to answer.
Okay, thank you very much, Wart, also for keeping an eye on the time. I think it was very interesting because this training is all about producing data. So basically what a soil laboratory does is converting a soil or a groundwater sample into data. And then therefore, I think it was really essential to show how to deal, or others how will deal with the data. And also I remember from Ilse's presentation that, yeah, the model is only as good as the input data. So this puts indeed the quality of the data and the essence of it in a good perspective. Okay, I will have a look at the chat, and I can reassure everyone here that this was the longest session of all the training modules. So for all the other ones, it will be shorter. But please, if you have any questions now, you can formulate it now to Wart or also to the other speakers. I don't see at this moment, Wart. Of course, all the modules will be given afterwards to everyone. So we have already given our email addresses, so they can contact us as well if needed. Okay, if I don't see any question here, we will resume the session and we will come back in more or less 1 hour and a half for the next session, a shorter session on soil sampling related to agronomy. So please, I would like to thank the speakers of this morning once again. So Wart, Ilse, Jan, thank you very much for giving this broad overview on fundamental aspects that we need to consider related to soil pollution. And then I think we will leave the meeting now and come back in more or less 1 hour and a half. Okay, see you and thank you once again.